prime and then divided by...
Yeah, there you go. Just divide all that shit. Do you see, I could throw more and more terms in there. Do you see how it doesn't matter? Yeah, there you go. That's my point. The process doesn't change just because there's more terms. All right, guys. Let's take a look here. So this is something we covered a little bit when we were going over the review sheet, I think, if I remember correctly. At some point we talked about this. You can always take an inverse trig and draw a representative triangle. The funny thing is, all right, do I want to get into that? No. You can always draw a representative triangle. It might not physically be possible, but mathematically it doesn't matter. I'm missing this side because to answer this question, I need to do y over x. So I'm missing the side. Thank God old Greek dude stole his followers' work so he can use that shit. So if I call this a squared plus 9 equals x squared, a squared equals x squared minus 9. Dear God, now listen. We've talked about this directly before, and it's okay. It's not okay, but I'll be fine that you forgot. And I think I told you guys that Calc 3 students do the same thing. And then I go to my weeping corner and I weep, and then I feel better. You cannot distribute a square root across subtraction because what are square roots based on? Multiplication. So they will only play well with multiplication. If that was the square root of 9 times x squared, that's 3x. More specifically, 3 absolute value of x. But I could then do it because I can distribute a square root across multiplication because that's what it's based on. It's not based on subtraction, it can't distribute. You can't play well with it. So then what's the answer, Jeff? That. It's not the answer, but it's the answer for what that side is. Yes, A is this. Therefore, what is the actual answer to the question? What's the tangent now? It'll be this over this, so it'll be this, the y side, over the x side. That's it. Now, I know at the moment that is not what you expected, and a few of you guys second-guessed yourself and then did some more shit. That is what it is. That's just what it is. And you're going to slowly start to realize that when you get that kind of problem, you should lean more towards, oh, that looks good, instead of, oh, that looks wrong. If anyone's going into Calc 2, this kind of thing is going to be a huge part of Chapter 7, the first chapter you're in, is this kind of expression. It's going to be relatively big in Chapter 7. But for right now, we're going to need this to do some stuff. What about this dumb thing? Oh, sorry. What's up?
Well, so it doesn't change, the way we solve it doesn't change because it's inverse? Or because it has the secant negative?
Oh, it totally. Why did the triangle exist that I drew? Because it was an inverse secant. Secant of angle equals ratio. Inverse secant of ratio equals angle. Therefore, I can draw a triangle whose secant would be x over 3. And then I could answer whatever question the crazy person doing the problem wants me to answer. Yes? Yes, with me? This needs to become a standard problem. Sort of like if I said, solve x squared equals 9. That's a standard problem, yes? We know the rigmarole, we know the sense. So this needs to be a standard problem. Trig of, inverse trig of shit. Draw a triangle, old Greek dude, give the answer, move on. Yes? Is that cool? Now, it isn't that right now, I understand. Because a lot of you guys, we don't really focus a lot on this, and we really should focus a little more because it does come up every now and again in mathematics. What's wrong? So here, I was given a ratio, so I know trig functions are all just ratios. So if I'm given a ratio, that's easy. I wasn't given a ratio here, or was I? Yeah. So if you ever have a whole number, yes, and y is a whole number. She's a whole expression, I guess, not a ratio. What's the triangle that I can draw then? What sides do I know? So if I call this theta, where's y?
On the bottom.
Careful.
it's appropriately enough, it's the y side. Yes? Because what's tangent theta? Y over x, thank you. Or if you're silly, opposite over adjacent. Sorry, not if you're silly. If you had a silly teacher. Where's 1 go? Where? What do you mean cosine? On the x, okay. And then to answer the question, the cosine question, what am I missing? Hypotenuse, because cosine is x piece over hypotenuse. Yes? So again, old Greek dude. It's, can you guys start doing this quickly? I would square both, add them, and then take the square root. So it's the square root of this guy squared plus this guy squared. And like we just discussed, square roots cannot be distributed across the distance subtraction because they're not based on this. Okay. So what are you doing up here? Some of you guys look stressed out, which is understandable. You're in a 6-week course. That is a normal human reaction. Okay. But is this feeling familiar? Do you guys remember doing this kind of stuff? A little bit, okay. Yes?
Wouldn't the 1 be where the y is?
No. Because what's tangent?
Sine over cosine.
Sure, which is even more fundamentally either y over x or opposite over adjacent because it's TOA and the dumbass SOHCAHTOA thing, yes? Are you with me?
Yeah.
So yeah, it's opposite over adjacent. Opposite over adjacent. Y goes here, 1 goes there. If it was cotangent, it would be the other way around.
But wouldn't you have to like flip it because it's -1?
No. Okay. Alright. Okay, I love this. A -1 power means what?
Inverse?
No. So multiplicative, reciprocal, yes. Flip. A -1 power means flip. What does this symbol mean? That is not a -1 power. It isn't a -1 power. It is another drunken midnight math person meeting where they're like, this just freaking what a negative. So that's why. Has anyone ever heard of arctangent?
Yeah.
Okay, I hate arctangent, but I understand what it's trying to do. It's like students get freaked out about the -1. They think it's a power. They think it's a reciprocal. That's complete bullshit. What does this symbol mean? Is that 1 over f of x?
No.
Hell no. What is that? It's the inverse of f, yes? So if f of x is x plus 1, what's f inverse? What's f to the -1 of x? If f of x is x plus 1,
X minus
f inverse of x is x minus 1, not 1 over x plus 1. It's not the reciprocal. It's not a -1 power. It's the inverse symbol. So this literally means the angle whose tangent is y, not the cotangent of y. That's completely separate questions, yes? Y is not an angle because it would be the output to a trig question, which is a ratio of numbers. Okay. Is that all right? Again, really, really bad decision making. Okay. And we didn't have much going on back then, so it's understandable that they would imbibe in certain things. Sometimes that led to decisions like this. Okay. Blah, 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 blah. Do we have what we need to answer this question now? The cosine of this angle? Yeah. Now, I don't blame those of you. In fact, a little part of my heart just kind of like sang for you when anybody who did the not conjugate, but rationalized the denominator. We're actually not going to do that with some of the applications we're about to do. We're going to let that be. But you could make it square root of y squared plus 1 over y squared plus 1 if you rationalize the denominator. Yes. In case anybody did, I have a little single cheer for you because that mathematically that's correct. The applications we're about to do, we normally leave it like this, believe it or not. Okay. Okay. Now, Jeebus. These are simply, I'm trying to solve for y prime. Y prime is a variable just like x is a variable. Yes? What is x? X. It's a variable. It's a number I don't know yet. What is y prime? It's a number I don't know yet. Yes? You guys with me? whatever number x is, that would lead to the slope being something, and I just don't know either one of those things. So they're both variables. I'm trying to solve for the variable y prime. What's my first thing I've got to do if I'm trying to solve for a variable when I have an equation? I want to get, well, I want to get all the terms with that variable in it on one side. We know this shit. Get all your x's on one side, all the numbers on the other side, except now we're just expanding our variables. Get all your y primes on, so what y prime is in the wrong place? Yeah, the 4y prime. So I'm going to add 4y prime. Dear God, they are not like terms, so I can't put those together. Become a prime. Those are not like terms. What the shit, Jeff? Math boy. Well, how many y primes are in that expression? That
2.
side? There's only one. There's one. There's one that somebody distributed. So if I just undistribute it, otherwise known as factor the damn thing, I'm almost done. What do I get when I take a y prime out? And how do I get y prime by itself now?
Divide by x squared plus 1.
Yeah. Now, the minute you do this problem, every problem like this must be easy. Period. Now, I know there's a lot less terms in this problem. I'm going to try to address this directly. And this is why I brought up, just to be a complete freaking geek, I'm going to bring Yoda up again. His whole point was, once you got the dumb power, Luke, you just lift shit. It doesn't matter how big it is, right? So, once you know to get the y primes on one side, you just do that. So what's kind of like the side that's already got the most y prime terms on it, in it, I should say. Which side has the most y prime stuff? The left side. So then I'm going to designate this as y prime's home. Is there a 4 little y prime term that's out in the cold, not home with the other y primes? All right, let me move him over, yes? Is there something that's not a y prime that's in the home that shouldn't be in the home? They don't know this guy. Yeah, they don't know this guy. Get out of here. But this guy, they're like, oh shit. Get back over here, man. Okay. So then I get 2xyy prime plus y prime sine y minus xy prime equals x minus y squared. And then factor out the y prime. Do you see how every problem like this is the same problem? Do you see that? There are going to be some with more terms. All that means is more writing. That's all that means. And while that does suck a bit, it's much better than that means it's really hard. No, it's the same level of difficulty, just more writing. Now I take a y prime out. What's left when I take a y prime? 2xy plus sine y minus x. And then what's the last step? Divide by all the shit you don't want. Shabow! You can make whatever sound effect you want to. You can write better than me, hopefully. That'd be great. Okay. Does anyone now, do you see how those two problems are the same problem? Yes. The more you understand what I just said, the more you understand math. Math does not necessarily look at the elements of a problem. They look at the template of the problem, like the type of problem it is. Those are the exact same type of problem. So I just say those are the same problem. They involve the same process. This is going to become a huge thing that we must, it's going to be like the second step of a new process we're about to learn.
Yeah.
And then number 3, we have logarithmic stuff coming up. We haven't even talked about what the derivative of natural log or what log's derivative is yet. Yes? So obviously we're going to do that. And to do that, we need the process this is going to kind of relate to. So at the moment, I'm not asking for any derivatives. I'm just saying break this up as much as you can. So what's the idea here?
Natural log.
Definitely not distribute the natural log. That doesn't make any sense.
Natural
This
log.
does not say natural log times anything. But I can do natural log of a times b, and I can rewrite that as natural log of a plus natural log of b. Now, if you stop there, you're technically fine because my instructions did say multiple logs, but there's one more thing I could do.
Bring down to 2.
Bring down to 2. Jeff, not pounds. Hi-ya. And by the way, I'm not picking on a damn person, all right? I know this happened for other people. Shit. Are those equal to each other?
No.
No, those are completely different things. Yes? This one's a b plus 1 in a natural log. This is a b in a natural log, and then add 1. Those are completely different things. Again, everybody makes that mistake at some point. What about part B? What's the main thing happening in part B?
Subtraction.
Yes, a division inside of a natural log that leads to
Subtraction.
subtracting. So I'm going to do this just to cut to the chase later. And then what's the last thing I could do?
You bring down the 1/2.
In fact, you know, we're going in the direction of me saying what's the derivative of this. Yes? I want you to notice something kick-ass about natural log. Do you see how this would be a chain in another? If I was saying the derivative of that, is there something inside a natural log?
Yeah.
Yes. Is there something inside of a 1/2 power?
Yeah.
That would be 2 levels of chain rule, yes? And again, you don't have to know that ahead of time, but you can see that would be true. What are we about to do that would make the derivative so much easier?
1/2.
Take the stupid 1/2 down. Now, isn't that a much easier derivative? Okay. Because you know that's where we're headed. Because that's what the whole first half of calculus is, just derivatives like crazy. So this last part is about, can you break things down to make the eventual derivative easier to do that we have to do? It's also related to one other thing we'll talk about when we get there. Part C is a little bit evil. If you just did natural log of top minus natural log of bottom, you missed something. Yes.
Do not factor out of x.
Yes, before you attack anything with anything, you just see if you can simplify. You can factor the top. Just to cut to the chase, do you see how this would be that, and then this is factorable? Yes, okay. So this would be x times x minus 2, x plus 2. And then the bottom, you can take x squared minus 9, and then that would be x minus 2, x plus 3, x minus 3, eventually. Jeff, we give you x there, yeah. And then what can you cancel?
X minus 2.
Good, so then I get natural log of x times x plus 2 over x plus 3, x minus 3. And now we can start doing some shit. Now watch this, you guys ready? What things are involved in division inside the log?
So the top.
No, what things are being divided? Let me say it like that. Inside the log, what things is being divided?
X plus 3,
X plus 3, x minus 3, yes? Those are going to be negative, because how do I rewrite division of parts of a log? I do it as a minus, yes? So the shortcut for this is, when I multiply things, I add. When I divide things, I subtract. This original problem would be a chain quotient. Yes? This would be a chain quotient. This is just 1, 2, 3, 4 one-step derivatives. So if I simplify shit before I attack it with calculus, things are much better. I keep saying that because it's a good thing to know. How you guys doing? You guys alright? Anything about any of those problems? Are you all able to do that on your own?
I don't quite fully understand how we get like so many different natural logs in the last stuff you've seen.
What would that be?
Natural log. I mean, like the numerator over the denominator.
No, just that, what you can see there. That would be ln of x plus ln of x plus 2, yes? Okay, so that's ln of x plus ln of x plus 2. And then these are on the bottom, but this would be ln of x plus 3, ln of x minus 3, but I'm subtracting those because they're on the bottom.
Right, okay.
That's all. So there's 4 terms inside. There should be 4 logs at the end.
Yeah, just because you
Good, because any factorized part in the log becomes its own log. Good, we got it. Yes.
We can't solve 2b further.
What do you think you could do?
The x's.
What about them?
X, the x on the bottom. I don't know, it just seems like it's.
So you can't divide x away because division is not the opposite of subtraction, right? If you want to do it, everybody would have to have an x, and then you can cancel an x. Yeah, okay. Nobody's got what everybody else has, so nothing cancels. Yeah.
For like this practice sheet, we had a question on a test that was like 3, where you asked us to break apart logs into multiple logs.
I will never do that. This is a prerequisite skill. So the question on the test will be, find the derivative of this. And then I'm hoping that you'll break it up so the derivative is easier to do. Now, could you do a chain product rule? Of course you could. I don't know why you'd want to. I'd much rather break it up. And now I have an easy derivative, instead of a chain product. You guys see that? We don't even know what the derivative of natural log is yet. Well, whatever it is, this would be a product inside of a chain, yes? This is derivative, done. If I simplify first, everything's so much better. This one would be horrendous. Are you kidding me? That's a quotient, chain, no. This is derivative, chain, yes. Derivative of the chain, but it's just one chain. It's much easier. So let's do this. I keep talking about what we're going to do. Let's work in the direction of actually figuring out what the derivative of the damn natural log is. So we can actually do a problem like this. We are not ready for it yet, though. So one thing we need to do before we get there, you brought no paper, did you, Joe? That's true. Oh, well, I'll be all right. And then we'll take a break here in a minute, if you want to. Where am I at? What have I done? Oh, yeah. What we're about to do, let me ask you this. Okay. If I just write this, yeah. Now listen, do something very specific for me. Don't do all the derivatives. Just apply the rule. What's the main rule here? Chain rule. So don't do all the derivatives. So like, how do I start this off? Yeah, derivative of the outside of stuff, yes? Times derivative of stuff, yes? You guys with me? All right, do the same thing for this problem. What you got, Jeff? Just the first level of it. Yes? 1, 2, 3, 1, 2, 3. There we go. I'll get there eventually. Yes? Sorry? Oh, yeah. Same exact idea, right? What would it be?
Cosine.
Times?
Stuff.
Now I'm going to ask you a really dumb question, and you're like, I saw you do shit. Where did 3x squared come from on my first problem? It's a really dumb question. Where did it come from? I didn't got it. From my brain, right? I made the problem. Where did tangent of 4x come from? I just made it up on the spot. You guys got it with me? What do you? Would it change? Can you? All right. Here's the big step. I want you to notice what is about to happen. Let me do one more specific one. What if I had put this instead? What would this derivative be?
Cosine negative stuff.
Cosine of stuff times stuff. Derivative, yes?
Yeah.
Now, each one of these I'm not done, correct?
Yeah.
But each one of these, that is the first step. Does it matter what function I put here? Does it actually change the first step?
No.
Let's see if you guys are really with me. You ready? So if I put any function here, do you understand what I just did? If I put any function, in fact, this would have been so much better. Jeff, this would have been a great place for that. Let me see if you guys are cool with this. Another way besides prime, I could do the d by dx thing, yes? You start to see why that's very necessary here. Because now I want the derivative with respect to x. What is y? It's a function of x. In fact, in this case, what was y? E to the x tangent x. In this one, tangent 4, blah, 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 yes? So this just represents the fact that as the teacher, I could put whatever the shit function I want there, yes? But would you all agree that these all say the same stupid thing?
Yeah.
No matter what that function is, what's the answer look like? The first
Derivative.
step look like? No, go ahead. You cosine
Cosine.
of
Stuff.
y times
Times derivative of y.
derivative of y, which I'm going to write like this to be a little bit better. Okay. Every single one of these says this, yes? That was this for the choice of y. That was this for the choice of y. Blah, 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 yes? This is a valid statement then on its own, independent of this other shit I just did. This statement by itself is true. Notice something really nice. Am I done with any of these three?
No.
Am I done with this one? Of course I am, because what the shit is that? I don't know. You didn't tell me what y was, math boys. That's as far as I can go. That's the beauty of what we're about to do is, if you realize it, is you have less work than normal. I don't even know what y is. So how can I do its derivative? I don't have to. I just have to write insert derivative here. I don't have to do it, because I don't know what the shit it is. I don't know if you guys are with me or not. Do you guys get the idea here? If I have something inside of another function, its derivative will involve a chain rule. I don't care what the thing is inside. The first step would look exactly the same. Okay, I like it. So, if I have, here, I'm going to do several things. The first one's going to be really, 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 really silly. If I have this, how would I take the derivative of both sides?
Power rule.
So if I do the derivative with respect to x of both sides,
2x equals u.
yeah, 2x, careful, no.
2x equals derivative of y.
Yeah. Which you could write as y prime, but I'm going to make dy dx. Do you start to see why it's important to say d by dx? Because what's this derivative with respect to y? It would be 1. So I do have to start being a little more explicit with what I'm taking the derivative with respect to. I don't know if you guys are with me. This is really silly what I just did. This just says y prime equals 2x. If y is x squared, y prime equals 2x. Now watch this. Now let's take the derivative of both sides.
2xy.
All right. What would be involved? What is y? What is y? What is y? Even more broadly, it's a function of x. You with me? So what rule do I have to use here?
Power of product.
Product rule. It's x squared. That's a function of x. Times y. That's a function of x. Product rule, yes? So that would be derivative of x squared times y plus, keep going, x squared times
Derivative of y.
derivative of y. Do you guys see that? When you see, they're going to be pretty, this is going to be, all right, Their instructions will be direct. They will say use in what's called implicit differentiation. Is this an explicit function of x that I've written? No. It's kind of like tangled up. Could you solve for y?
Yeah.
Totally. So I'm going to go further with what we're doing here. Just go with me. So everybody kind of get what's happening here? This could be sine x. If it was sine x, what would its derivative be? 2x sine x plus?
Cos.
Yeah, where'd this come from?
Sine.
That's the derivative of this piece, yes? Where'd this come from? So those are the same dumb thing, yes? That's exactly the same as this. I was just more explicit in what y is, which is why we call this implicit differentiation. I don't know if you guys are with me. So, National Geographic has implicit violence. I don't know if you ever watched National Geographic. When you were a little kid, the thing would go behind a bush, and the bird would come down, and behind the bush, horrible things happen. But if you grew up and you watched some horrific movie, that's explicit violence. Yes? What's up? It's just in your face. All right. You guys do it. So implicit means it's not in your face. I haven't told you what this function is. What could it be? Anything. But I do the same thing because whatever it is, whatever function it would be, I would do that. So I just do the same thing. It doesn't matter what function it is.
What if product will be the derivative of the first one?
Yes, derivative of the first one times the second.
Right.
Plus, leave the first one alone, derivative of the second.
Oh, okay.
Yep, good. And what did we do this side? What did we just do to this side? What did we do to this side? And what do you have to do? You have to do the same thing to both sides, yes? Always. So what's the derivative of x? You ready for this? This is silly. You ready? I want to do d by dx x. What's dx divided by dx?
1.
There's a whole other reason why the derivative of x is 1. Because it reduces the stupid 1. Okay. I love you guys. I love how some of you guys do my side eye. I love it. A little side evil eye going on.
Break.
Not quite yet. I want to finish this problem and then we'll do a break. I hear you though. Now here's the beautiful thing. On this problem, what is dy dx? Do we know it?
No.
No. Do we know it?
Yeah.
Yes, 2x. Do we know what dy dx is here?
Yeah.
No. What's dy dx equal? No.
2x.
This equals 1. What's dy dx? Do we know yet?
No.
All right, we got to solve for it. Oh.
We're going to use natural.
No. What were we doing in these problems?
That.
Solving for y prime, dy dx, yes? Okay. So I got to solve for dy dx. How do I do that?
Isolate.
Here, let me write this. Oh, shit, Jeff. You need more paper. You write this a little better. We're almost there, yes? How do I solve this for dy dx?
Isolate the dy.
Well, yeah, get the term with dy dx in it by itself.
So subtract 2xy.
And divide by x squared.
Divide by x squared. Hi-ya. One thing I want you to notice. In the past, when we took a derivative, how did you find the slope at a point? You just had to input the x part, yes? When you do implicit differentiation, I have to plug in the entire point. I have to plug the x part in and the y part. Now this specific problem, I didn't have to do implicit differentiation at all. Because could I solve this for y?
Yeah.
What do you get when you solve this for y?
Y equals negative x squared plus
Huh?
x squared
Sorry,
minus x.
that was me. What?
X squared minus x.
No. How did I solve for y?
So,
Divide.
oh,
Yeah, so you get 1 over x. Is that cool? What would y prime be then?
1 over
Here, let me write this here. Okay, yes?
yeah.
What's y prime?
Negative. Negative.
To the? Negative 2, or other words, negative 1 over x squared. Yes? Now look, this is dy dx, yes? That's dy dx. Are these the same?
No.
Yes. You ready?
But
What was y? What was y?
1 over x.
1 over x. So if I rewrite this, what's 2x times 1 over x? The x is?
Cancel.
What's 1 minus 2?
-1.
Are they the same?
Yeah.
Okay, so before we take a break, I want to show you one thing. It's going to take me 5 seconds, yes? When I get there. I'm not there yet. Do you guys see how if I can solve for y, go back to the problem, Jeff, I obviously should, but if I didn't notice that, it would still actually represent the same answer. It just doesn't look it because it's got y instead of what y is.
So is universal y 1 over x? Is that also y is?
Hell no. What's the only reason y is 1 over x here is because I solve for y. If I divide by x squared, don't I get 1 over x?
Oh.
Okay.
Okay.
So if I have a problem like this, let's do that. Yeah, there we go. Look at that. Can you solve that for y?
Yes.
Teach me. I am ready. I am a humble man. If you could do it, I am ready to learn. Feel like that. Have anybody ever saw the movie Kung Fu Hustle? See, at the end, he's like, teach me. No, okay, you're fine. You should watch it because it's one of the best movies ever made. Do you guys see? Can you guys see? If I divide by x and take the inverse tangent, didn't I just make another y piece really stuck? Can I ever unstick any y piece? If I subtract and divide by x squared, I didn't get y by itself because there's still y shit stuck. If I take the natural log of both sides, get him by itself, I've made other y pieces get stuck in a natural log. Now listen, I need you to understand what I'm saying. That is a valid relationship. Its graph would look funky as shit. Its graph would look something like, wow. It could do anything because it's got all this mixture of x and y. I can't get y by itself, but could I find the derivative? Could I find dy dx?
Yeah.
All day. No matter what this function looks like, do you agree with me? In fact, when you come back from break, we'll graph some of this on Desmos. Do you agree with me, even if it looks like this? Do you agree that somewhere at a point there's a slope?
Yeah.
Yes. So I should be able to solve for dy dx, and I can. The way we just did, we can solve for dy dx, because there will be a slope. I have shoved a lot of stuff in your head. Let's take a break. Come back at 5 minutes, and then we'll keep going like crazy. Okay. Let me know if you have any questions or anything wrong in your grade sheet. Why is this? Yeah, it doesn't pass the vertical line test. So a decent number of implicitly defined relations will not be functions because they won't pass. What is happening with you? There we go. Sorry, I'm wrestling with my phone. They won't pass the vertical line test. Do you agree with me that every point on the graph has a slope?
Yeah.
What up? Ugh. Let me see. Is there any point? No, screw it. So if I found the derivative of this, I could then plug any point in to get the slope at that point. What would you estimate the slope is like right here? To me, it looks like maybe 1. If we go, maybe it's a little more than 1 if you kind of look at it this way, right? A little more than 1. Do you guys agree?
Yeah.
Do you guys see what I'm saying? It does not matter that it's not a function. It still has a slope. And that's what calculus, the first part of calculus, is all about. Calculus helps me find the slope of something at any point. And now we're expanding it. It doesn't even have to be a function. I can see there's a dumb slope there. That's what calculus is all about. So let's do this. Can you guys take a minute and try to figure out that guy's derivative? I don't need the parentheses there, by the way. I don't know why they're there. I don't want to make it look worse than it is. There. Also, real quick question. Could you solve for y easily?
You can factor out a lot.
Sorry.
No, you
I
can't.
just love them. Of course you can. What are you talking about?
You could solve for y. It would not be nice. But can you guys see how there's a y and a y squared, which automatically makes it at least very hard to solve for y. You could use something related to quadratic formula here. Do you want to?
No.
Do you want to? Do you want? No. Good Lord, no. And whatever the shit I get, I don't want to take its derivative. It's going to be horrendous. So I'd much rather just leave them alone. All right, keep going. I'm sorry. Keep talking. Take this, guys. Find dy dx for this. Oh, I forgot to get paper. That would be so helpful. I have paper. Yes. Do. Have to let it linger.
For the last one. I mean, for the whole thing except for the last one, use product rule.
Product.
Yeah, but the x3 and the x4 is the y.
For what? X cubed is just a power rule.
Minus 3y.
Minus 3y is straight up derivative of y,
Right.
which is dy dx. Yep.
Maybe you can because it's
For the last one,
No, there's no nice point, is there? Well, it's almost a nice point. I don't know. All right, let's see. So this really, if you have any issues with any of the general derivative procedures, you're really gonna have trouble with this because this is everybody. This is everything, including this little evil, the problem's like, I'm not gonna tell you what y is. And so on top of needing to know all of your quotient, product, chain, you also have to go, oh, sometimes it's just not gonna tell me what function it is. But that's actually nice if you let it be. What's the derivative of x cubed?
3x squared
Thank the gods. What's the derivative of 3y?
minus 3.
dy dx. Derivative of y with respect to x is the derivative of y with respect to x. That's insane. And what do I have to use here? Product rule. Derivative of x is 1 y squared plus x. What's the derivative of y squared?
2y.
Good start. dy dx. Why is that? Was what is y again?
You don't know?
Function of x. And what do I have it inside of? A squared. What rule is that? Chain rule. What's the derivative of something squared? 2 times it times the derivative of the inside. Do you guys see that?
So you use chain rule when you got the 2y, dy over dx is chain rule, but that's the outcome?
That's chain rule, yeah. Huh?
Yeah, that's like, but that's, you say that's like the outcome of chain rule?
Totally. Yes. Yes.
You just get the-
Derivative of something squared is twice something times derivative of something. Good. And of course, what's the derivative of 0? 0. Now, what was it I was trying to find?
dy dx.
dy dx. Good. So how do I do that?
You move everything that doesn't belong to the other side.
Yeah, and I want you to notice, this is not that big of a deal. In fact, I don't care. What do you want to move where? I was going to show you to do something specific, but what do you want to move?
The 3,
Go ahead. It's all right.
the 3 dy dx.
Oh, good. All right. See, that's what I would do. Move that over. What else should come over here?
The other one. The
2xy.
Because then that leaves all my stuff that does not have a dy dx. And I've got now all my stuff that does have a dx. Dy dx. Jeff, it's hard to talk, and apparently it is for me anyway. Be quiet. And now, why did we do that?
So we can factor out.
Yeah, so I can factor the dy dx out. And then
Divide by the 3 minus 2y.
now, okay. So on one level, this is unsatisfying. And you might not even know why it is. And it's because, what does that even mean, Jeff?
What does that even mean?
So if I have a point that my graph goes through, and I input the x and y part, this will tell me the slope at that point. Like I said earlier, when I have explicit functions of x, I only have to plug the x piece in to get the slope. When I have implicit functions of x and y, I have to, not function, but I have to put the entire point in. So let's go back real quick. I'm going to pick a specific actual point. And I think I found a decent one. Where were you? There. That's not too bad. 1.05.46. You guys see that? I'm going to round it just a bit. Yes? 1.05.46. I'm going to write that down. Okay. Now, can you guys, if you can't, oh man, you're going to have an even rougher semester going forward. Can we all handle that that's not the prettiest numbers? Who gives a shit? How do I get this slope?
Plug it in.
Plug it in. So where do I put 1.05?
On the x.
In the x. Can somebody help me actually figure this out? Let me see if I can guess. 2.5. I'm gonna be a little less. I'll do one. Oh, that's squared. Oh, I see.
Yeah.
Oh, it's 2, and that's basically, so it's like a little more on the side. So I'd say 1.54. No, I didn't square that, did I? Yes, I did. Didn't I? I think so. I don't know. I'm going to pretend like I know and say 1.54 is the answer. Hopefully everybody's putting their parentheses in the right places and such. You got to tell your poor little calculator, oh shit, poor little guy. He's almost dead, that poor little guy. How you doing? You're perfect, damn. Parentheses, so I tell it what the top is. That's, oh, Jeff, there you go. Parentheses, so I tell it what the bottom is. Whoops. Let's see how far off I was. What did I say, 1.54? I can live with that. That's good for government work, 1.73. You guys with me? Now, we're gonna go one step further, because of course we are. So we got that this, when I have, here, you ready for some notation? When I evaluate this at 1.05.46, we get 1.73 roughly. Yes? Now, just to close the loop on this, everybody with me? This is exactly the same shit we did earlier. Instead of just plugging an x value in, I gotta plug the whole damn thing in. Because my function that describes my slope, not function, but my relation, needs an x and a y value. Is that simple? Can you get the equation of the change line? Do you have a slope? Do you have a point? Are they what you wish they were? Not exactly. But can you do it? Of course you can. How do you do it?
Use the formula.
What formula?
The y minus.
You're crazy. All right. So sorry. Y minus the y piece equals m times x minus the x piece. So let's see, y equals 1.73x. 1.73 times 1.05. Oh, that's the dim one. Plus 0.46. That's negative 1.36 roughly. I'm gonna keep rounding. Why not? And if you guys don't trust me, do it yourself. Does that seem right? Something seems wrong with that. Let me see. Did I put that in there right? I did. Oh, okay. That's right. That's right, Jeff. Okay, is everybody with me? If I graph this equation, all right, this is where everything, I don't know if anybody's actually doing the whole thing. I'm hoping I did that right I'm pretty sure I did. So when I graph that line, what should happen?
Like, you should get the. You should get the tangent line.
I don't know why I picked the same color. That's weird. How do I do this? Oh, there it is. There, that's better. Hee hee hee.
That's the same color.
Right?
Color.
Oh, I'm sorry, buddy. I gotta remember that. Christmas is just a bland, just nothing. You guys, does that look like what it's supposed to look like? That was the point we were interested in, right? That's the point that I picked. And sure enough, it does exactly what we know it should do. Now, obviously the derivatives are harder. Yes? I'm not trying to say anything about that. They are harder, but they all mean the same thing they did before. I could do all the same shit we did before. I could just have much funkier graphs. In fact, I think some of you guys were paying attention earlier when I was messing around with different formulas to put here. What have I done wrong? Oh, there. That is an example of a implicitly defined function. It's not, I keep saying function, but it's implicitly defined relation. That is trippy as shit. That looks like yarn and then this one little squiggly piece connect, like I fell on the floor and this is how it fell. Do you all agree every single point has a slope? So I could find dy. Would that derivative be much harder to get?
Yeah.
This is a product of three functions, and this one involves a chain rule, so it would just be more and more shit to write. So I am very mindful that I don't want to just create a problem that's hard because there's so much to keep track of. That's dumb. That's busy work, right? This is maybe the kind of largest, because once you do this derivative, there's going to be a lot of parts of it. And I don't want you to get something wrong just because you mistranslated something or moved it and didn't bring a negative sign, whatever the shit, yes. That's dumb. But you do have to show me evidence that you could follow the chain of derivatives that you have to do and you can keep track of it. Okay. Maybe.
So
Isn't that kind of neat? Anybody think that's at all neat that this is an ugly function, but is it really that big? Has it really got that much going on? No, but look at what it leads to. Look at this shit. I didn't know it was going to look like that. I'm intrigued. Go ahead.
Because you can't separate the x's and y's, like you were saying.
You can't do what now?
You can't separate the x's and y's, like you can't isolate.
Exactly.
That's what happens.
That's what happens. The fact that I can't get y by itself leaves the door open for this to not be a function. You all agree this is very much not a function? This is so desperately not a function. Yes?
Yeah.
Because any x and y value that makes that true is a point on the graph. And the fact that I can't make y a function of x, y doesn't necessarily depend on x. They kind of depend on each other in a way. But any point that makes that a true statement is on the graph. And there are many more points that could make that a true statement than like a regular function could. I don't know if you guys are all with me. I guess, okay. This is a huge kind of step we've just taken. Now, implicit differentiation is not going to suddenly become what all math is. No. In fact, it's going to very quickly kind of like take a back seat. But the idea of parts of it being a function of the other parts, that's the bigger idea that is going to come back later. I'm not sure if you guys are with me or not. This isn't suddenly what our class is going to be. This is kind of a contained idea, but elements of it will go forward. Okay. You're not helping, Jeff. All right, I'll stop. So, let me do this. What was on this other sheet? No, that's that one. Oh, on the reverse of the sheet I gave you guys. That's where that is. This guy. Okay. Yeah. Go ahead and do the first three up there. And again, you can work with other people. You can work by yourself. All right. X squared y, I don't know. I think it's my favorite. You see it everywhere today, but so x squared y is a what rule? Product rule. Derivative of x squared times y plus x squared times the derivative of y. Now, what's the derivative of cosine stuff? Negative sine stuff. So this becomes plus sine stuff times derivative of stuff. That's chain rule. That's all it is. That's all it is chain rule. Whenever you see a y, imagine it could be x squared.
This kind of a small thing, but would it not also be correct to put dy dx in parentheses instead of sine y in parentheses?
Yes. Because as long as they don't put y, dy dx in parentheses, I know it's not inside of the sign. This is, in a way, this is being a little more careful. But your way's fine. Yeah. And then what's the other side become? Nope. What did I do to this side? Took a derivative. So what do I have to do to that side? Take a derivative. So that's one of the biggest mistakes I see is students only do one side. We've known forever that whatever you do to one side, you have to do the other side. Now some of you guys, it feels like we should be done, but we're not. We just started. How do I get dy dx by itself? What do I have to move?
You actually subtract
Take the 2xy.
Yeah, 2xy, it doesn't have a dy dx, so it shouldn't be over there. So we kick it out. Are you guys cool with, do you guys see if I get rid of that, I could take a dy dx out of the remainder?
Yeah.
Because then what's the last step?
divide by x. Right?
Divide by shit you don't want. And then that's my answer. Very quick little side note. Can you figure out a point that this goes through?
Plug in.
Plug what in? So, listen. I would normally try to plug a 0 in, right? If I plug a 0 in for y, that 0 minus 1 equals 3x, and then I could figure out x. But do you see how, in general, if I wanted to make a table of values, do you see how the difficulty is ramped? Not even up to 11. It's ramped up to 111 on a scale of 0 to 10. Yes? Because they are present in all these different places. Forget about it. If you make y pi over 3, no, I don't want to do that. All right, I'm just trying to point out that I'm not going to make you graph these by hand. That would be incredibly evil, and I'm just not there yet. I thought I would be. I'm a little behind. I think 10 years ago I was like checking with 10 years, and I'm still not there. Damn it. All right. I hope the council is lenient with me. Is everybody kind of cool with that first one?
Yeah.
You can start to get the idea of this. Why, if this helps, just always think y could be cosine x. And then, of course, if y was cosine x, there would be a bunch of chain rules. There would be all this shit. Everything we just did would happen. It would just be more explicit. Instead of dy dx here, I would have negative sine x there, right? But this is even better because I don't have to worry about that part. I just put dy dx. All right, so how does this work? Yeah, derivative of the outside is cosine times derivative of the inside, yes? I'm just gonna put prime just to mix my notation up. Why not? Now, real quick, one thing I should have done for myself that I can still do right now is how should I kind of rewrite this just to make it easier to look at?
Negative 1. Oh, negative 1.
Y to the negative 1. Good. So what's the derivative of this?
Y to the negative.
Yeah, the negative comes down. Makes it plus y to the negative 2 times.
E to the no times.
What's the inside function? Yes? Every time you take a derivative of a piece that has a y in it, there's going to be a dy dx as a result somewhere. Either there's a chain rule or it's just y that becomes dy dx. You guys see that? Now when I say that, I get students that start to just throw dy dx everywhere. Just to cover their ass maybe. But no, that won't work. The inside function there was y. That's a function of x. So it needs to have its own term. It's chain. Yes?
Yes.
And then what's the derivative of e to the x?
Because look at sine. It's not just sine x.
Yes! It's the best part of this. The best part of calculus class is e2. Okay, I'll stop. We still have to do this. This poor little guy, I'm going to give him his own room here in a minute. What's the derivative of xy?
1.
Yeah, derivative of x times y plus x times the derivative of y. Yes, it's just straight up product rule, yes? Look at that. That's a thing of beauty. I love it. Now, what the shit do I do with this? Can I subtract cosine xy from both sides? Hell no.
Just like
I could divide, but that would make this term become really disgusting.
yeah.
Yes? So what should I do? It's the thing that you would naturally be, where your eyes drawn when you're trying to solve an equation. You look for the parentheses because that's where you distribute. Right? So I'm going to distribute the cosine. Holy shit, how did I fit all that? I don't know. So it's cosine times y, bam, cosine stuff times this stuff, bam, and then plus that stuff, bam, and then equals that stuff, bam. So what piece is in the wrong place? There's only one guy that's in the wrong place. Yes. So I'm going to subtract him. So I get, let's see if you guys are cool with this. That's gone, yes? I could take a dy dx out in front of x cosine xy plus y to the negative 2, and that equals e to the x minus this business. Oh my god! And then I just divide by all this shit. So I need you to notice how your I've said this kind of thing before, your brain kind of balks at this because there's so much. But most of this is just me rewriting it over and over. Which isn't the best, but at least it's not stuff I'm directly working with, so I have a lot. But no, I have very little going on. I'm just rewriting a lot of this shit.
Wait, let's just to reiterate.
Yeah.
You use the chain rule for the sine xy, but then for the negative 1 over y, you just use the power rule for that, right?
Well, I use the chain rule for this, for sure.
Yeah, and then the negative.
I use the chain rule for this, definitely.
How?
Stuff to the negative 1 is -1 times stuff to the -2 times derivative of the stuff. That's the chain rule right here. That is there because of chain rule.
So did you use two separate, two different types of chain rules, one for sine x, like a chain
No,
rule?
no, no. There's no such thing as two separate types of chain rule. So why does this need a chain rule?
Because it's x, y.
Because the stuff inside is more than just x.
Right.
Why does this need a chain rule? Because what's inside in -1? More than just x.
Okay.
That's all, that's it. Chain rule. Believe it or not, chain rule is always the same thing. It's always the same. Just the inside gets its own term. That's all chain rule says. You guys look appropriately excited. Divide by all this business. Oh my god, and then we're finally done. Die! Okay. Oof. Go ahead and try the third one, the part C, I think. Try this one if you haven't done it yet. Does anyone know what that would look like if I graphed it? Anybody?
Circle?
Circle. Beautiful. We can subtract 2y, complete the square to figure out what the radius. We're not going to do that at the moment. Go ahead and take that guy as the part C.
Can we show them the equation that we just did?
I guess so. That's a negative here, right? Poor little guy.
So it's actually this not big enough. So we go
So 1.73 times 1.05, that's what that is. That's 1.05. That, and then you add 0.46. Oh, it's a negative though, yes, it's a negative. So it's negative 1.73 times 1.05, yes. And then you add 0.46 to it. Add 0.46. Yeah. Sure. You left the negative on it.
Where am I going with this?
You took the derivative of one side, not the other.
Right, but how do we,
Also,
that would be, would that just be?
isn't this stuff squared?
Yeah.
So it should have a chain rule piece at the end. Yeah.
This was 100? 1.13. This was 100?
That's a negative right there.
Yeah.
So it's 1.73 times negative 1.05 is negative this, and then add 0.46. I didn't. I just put the negative on the number. I know it's going to be a negative answer because one of them is negative. It doesn't matter where I put the negative. Did you finish?
I don't know. I'm kind of right here now.
So you're saying it'd be this?
No. Nope. What's the derivative of something squared?
Don't you use the chain rule for it?
Squared is right down, and then it's one.
So like, what's the derivative of e to the x squared?
E to the x.
It would be 2 comes down. No, let me make it less weird. What's the derivative of x squared plus 7x squared?
It'd be two will come down.
2 comes down in front of stuff
Times stuff.
to the first power times,
Derivative of stuff.
right?
Yeah.
So let me replace this with y. That means there would be a y here and there would be a y there. So it would be 2y times y prime.
Yeah.
Or, you know, dy dx here.
There's the 2y on the other end. That just becomes 2, right?
No.
2.
Because what's the derivative of y? dy dx.
Yeah. And so it would be 2 dy dx.
Yes.
And then you move it to the other side and factor.
Yeah, then you start trying to solve for dy dx. Hey guys, real quick. Go with me for a second. I'm going to take the derivative of both sides of this, yes? What am I going to take the derivative with respect to, normally? Respect to x. So I'm going to do d by dx of this side equals d by dx of that side. This becomes dy dx. Is that cool?
Yeah.
This becomes dx over dx, which is? There we go. Okay, so that is why dy dx shows up as often as it does, because we're taking the derivative with respect to x. dx goes to 1. So it's not going to show up as much. dy dx is not 1. I don't know what the shit it is. In fact, that's what I'm trying to solve for. Okay. Now listen. Again, my tone is trying to convey that this is not as hard as it seems, but I also want to say this is some freaky ass shit. Yes? It just is. This is freaky. This implicit differentiation is weird. Does anyone agree with me? Yes, it totally is. I want to really make sure you understand I agree with you. It is weird. Now, obviously, I'm weird. So I think this beautiful little tears of oh, so beautiful.
Then you factor out the dy dx.
But I do want you to understand, no matter what my tone is, this is not intuitive.
What did you do?
This is not, you should have been born knowing this. They pat you in the butt and you're like, no. Then you start to cry because you don't have enough calculus. You need calculus. Where is it? Sorry. Shut up, Jeff. So if I look at this problem, I can identify where my dy dx is going to be a part of the answer there, because those two have y's in them. This one is just
2x.
What's the derivative of stuff squared?
2.
2 comes down in front of stuff to the first power times derivative of stuff. There, yes, chain rule. Equals. What's the derivative of y?
2.
In fact, if you really want to get down to it, what's the derivative of y? It's 1 times the derivative of the inside, which is just silly. But it's just dy dx. And what's the derivative of 3?
0.
Good. That 3 sometimes survives. Don't let it. Kill him. He's dead. Yes? He wants to be dead. Existence is pain. Please kill him. Okay, Jeff, so. Sorry, I'm going a little loopy. Now I do what I always do. What's in the wrong place?
The 2y.
Yeah, this guy's in the wrong place because there's the thing that without dy dx in it. So let me get him over there. He's scared of that guy. Doesn't like the look of him. I can kill all the 2's, yes? I'm just going to kill all the 2's. Just die. Just go away. Just die. So then I get x equals dy dx minus y dy dx, yes? So then I get x equals, take a dy dx out, and what do I get? Good, 1 minus y, and then divide by 1 minus y, and I get my derivative. Okay. Chumbawamba. Now,
Wait.
B, hey, go ahead.
How did you get rid of the 2y?
I didn't. The y is still here. I just killed the 2. Everybody's got a 2, so I can divide by 2.
Oh,
Yeah. So he's still here. It's just now he's a 1y instead of a 2y.
How do you got minor? Is that a fault?
That's trying to be a y. Trying desperately to be a y. Is that better? I don't know. Yeah.
Oh, yeah.
If you wanted to be able to read what your teacher wrote,
Thought
you've
that was
chosen
four.
poorly. Oh, okay. Now, real quick, being me, I'm gonna push this. Do you guys remember how I just said a second ago how you can? I'm just gonna work with the original. Just go with it for a second. Half of -2 is -1 squared is 1. I'm gonna complete the square. I add 1 to both sides. Then this will factor like this. Does anyone know anything about that circle? What's the center of that circle? 0, 1. It's been moved nowhere on the x-axis. It's been moved 1 up in the y direction. And what's the radius? 2, because it's x squared plus y squared equals r squared. It's been if it's been unshifted. So this is a circle. Center at 0, 1. Radius is 2. Center is here. Radius is 2. So there's a circle. So where is y1 on the graph? Where's y1? Right here, yes? You with me? What's the slope right there?
2.
Undefined, infinite. You guys with me? Because isn't that slope just going straight up? It's only rise, no run. Rise over 0 is an infinite, yes? And what do you get when you put a y equals 1 in? On the bottom, which gives you undefined slope. So at y equals 1, the slope is undefined. Maybe? Yes?
Is anything equal to y be undefined?
Anything?
Equal to y undefined.
No. If y is 1,
Oh, fuck.
it's undefined.
Because
If y was 1/2, would I get a 0 on the bottom? If y was 1/2, would I get a 0?
Oh,
on
no,
the bottom?
okay, further.
But from the picture too, there's only 2 places where the slope goes infinite. Here and here. It almost like a little robot dude looking at you. Alright. Okay. How are you guys doing? You guys alright? You guys look tired. I understand. Okay. Coming back to this here. Number 2. How would I do this?
Plug in.
Well, if I plug that point in, I can verify it works.
I mean, define derivative.
Derivative, okay. So it's the same old thing. Find the equation on the line. We've done tangent line equations. They can never fundamentally change. They're always going to fundamentally be the same thing. Get the slope, get the point, make the equation. Yes. That can't change. The way that we get derivatives, the way that we get slope, can change.
Is the
That's the problem.
7xy chain rule?
No.
Or no, that's just
Is that a problem?
Product rule, yeah.
7x
what's-
is a function and y is a function.
Totally. What's the derivative of x cubed?
3x squared.
Derivative of y cubed?
-3y.
In fact, look, I'm sorry guys, give me a second. 3x squared times the derivative of the inside. Do you see how dx is 1? Minus 3y squared times the derivative of the inside. dy dx is, I don't know yet. Do you see what I'm saying?
It's always chain rule.
This shows you why this doesn't show up when the inside's just x. It all day shows up if the inside's different from x. I don't know if you guys remember this, when we first learned chain rule, I said, when do we do chain rule? Always. What's the first rule of chain rule? Always do it. It's just, when does it show up? When's the only time I have to worry about doing it? Is if the inside's more than just x. So I got 3x squared minus 3y squared dy dx. And then this is product rule, like you said. So it'll be 7 times derivative of x times y plus 7 times x times the derivative of y. All right, so this is a classic little equation. Get my dy dx by itself, move all the stuff together that goes together. So I would add this over just to keep stuff more positive, but it's up to you. And subtract this guy. So I would add this guy over, subtract this guy over. Let me see if you guys are cool with this. Here's what I do. You ready? I write this side over the coefficients of that, because that's what's going to happen. If I take a dy dx out, I'm going to have this plus this. I'm going to divide by it. Hey, I'm going to get here. Is that all right? You don't have to do what I do exactly. Now the 0.42, that is an actual point. If you plug it in the equation, it works. So how do I get this how do I get the slope at that point? Plug in 4 for x and 2 for y. It's crazy. So if I want to get this at 4.2, I want to get this at 4.2. I just plug in 4 for x and 2 for y. I don't know why I did that one and not the other one. Are you guys with me? And then it's just, you know, computation crap. Did I do that right? What's up?
Are we gonna find the m?
Yes. 48 minus 14. Yes, is 34. Over 12 plus 28 is 40. So I get 17 over 20. That's exciting. So how do I, I'm sorry. Just imagine a student like, is he in the same class I'm in? How do we get the equation of the tangent line then? Do we have a point?
Yeah.
We do? Do we have a slope?
Yeah.
We do. So y minus the y piece equals slope times x minus the x piece. 17/20 x. 17/20 times negative 4 is negative 17 over 5. Plus 2 is plus 10/5. It's negative 7/5. I almost don't care if you follow it, because that's just a bunch of adding fractions and crap. Yes? I don't even know if I got that right. I think I did. So if I use Desmos to plot the original function and then I applied this function, it would look exactly the way it should. If you touch the thing in the right place, it would go with the same slope. Okay. Now we can't do the next problem yet. So let's do this. We don't know. All right, let me stop for a second. Sorry. Everybody got what they want from that?
Yes.
Okay. So I think you guys must have caught on by now that what we keep doing is do we know more functions than we know derivatives of functions? Yes, we know a lot more functions than we know derivatives of functions. For example, the most immediate next thing to look at would be a logarithm. Yes? So how the shit? So here's what I'm saying. If I have this function, I'm just going to do every log base b of x, yes? I want to know this guy's derivative. One option that's always available to us is to do what? Limit definition of derivative. Does anyone want to do that?
No.
You want to investigate limit is that h goes to 0 of log base b of x plus h, but no, I don't want to do that either. Now, to be honest, it is kind of neat, but we don't need it. We're better than that. Go team. Could you rewrite this in a different form that we know the derivative of?
Yeah.
What form can you rewrite logarithms in? Where's my people that were in my class last time? It's the washing machine. I'm going to put this into the washing machine. It's b to the y equals x. b to the y equals x. Those are equivalent equations. Do we know how to take the derivative of an exponential?
Yeah.
All day. The base is an e. Who gives a shit? What's the only thing I have to tack on if it's not the base e? Do you guys remember? Do you guys remember? What do I tack on? Like, what's the derivative of e to the x?
E.
E to the x. What's the derivative of 3 to the x? Good. So when the base is not e, I take the natural log of the base, and that's the adjustment for the poor little dude not being little Mr. Perfect e. Yes? Okay. What's the other thing going on here, though, if I take the derivative the way it's written?
There's a.
Is it written explicitly as a function of x right now? Oh, so it's implicit. All right. The derivative of b to the y is itself times the natural log of b, the base, times, you can do it. What's the inside function?
Y.
So what do I multiply by? And what's the derivative of x with respect to x?
1.
Yes.
You chain rule the b to the y, right?
Do it again.
You chain rule. Use chain rule.
Where? I'm sorry.
For b to the y, you use chain rule.
I use chain rule, yes, because the inside function is more than just
Yeah.
x, yeah. It's a function of x, it is. Is everybody semi good? All right, keep going. dy dx equals. This is really almost too easy to believe, yes? How do I solve for dy dx? You just, I don't subtract a damn thing. What do I do? Everything's multiplied, so I just divide. Can somebody help me? What was b to the y? B to the y kicks so much ass. What was b to the y?
Log b of x.
No.
B of y not just x.
B to the y is x, see? Chippa-chippa-pow. Oh god. So, whatever the base of the log is, if I have log base 7 of x, let's try to apply this rule. If I have this function here, we used implicit differentiation just because I can rewrite it in terms of a function I know how to take its derivative. But then I was forced to do implicit because I shoved y into a function, so I got to use implicit differentiation. The end result is a straightforward derivative. It's not like implicit. I derived it using implicit differentiation. This I can just apply. So what is the derivative of log base 7 of x?
Supposed to be 7 1.
What does it say? What's the rule say? Huh? You don't know. Okay. So if I have log base b of x, the derivative is 1 over x with an ln b on the bottom.
So 1 over 7 L.
No, come on.
1 over
X ln of
7.
hey. Hey.
You got there, Dan. You got there.
We got there. What does that mean then for natural log itself? Like if I have this. Sorry, go ahead.
Then the derivative of natural log 1 over x. 1 over x.
Yeah, let's do it. Let's do it all the way out. You ready? We're going to use exactly the rule, and then we're going to see that it's going to simplify. 1 over x ln. What's the base here?
X.
No.
1.
10.
No.
2 point.
E.
Where did he come from?
I love you guys so much. So, real quick. Okay, just a really quick side note. Do you guys agree with me that this is a log?
Yeah.
It is a really strangely written logarithm, yes? In fact, we write it that way because we call it the natural log, and that leads to really dumbass jokes. Math jokes are always dumb, but I love some of them. If I, how do I say this? Oh, what was the issue that just happened? What just happened? Let me see.
How did he got B?
Oh, that's right. I got you. Log base 2 of x, log base 3 of x, log base 4 of x, blah, blah, blah. Yes? Yes? Here we go. You ready? It's kind of like cube root of x, 4th root of x. Yes? What is this?
Square root of x.
So what do we understand is here? Why didn't we just put a 2 there? Because math people were lazy, and a lot of us don't write well, and we thought, we'll just let everybody know if there's no number there, it's understood to be a 2. Yes? So if I see this, did I put a base there?
No.
What's our number system based on?
Tens.
Yeah, why is our number system based on 10? Just no idea. I have no clue. We'll never know why our number system is based on 10. So when I see a logarithm with no base indicated, I know it means 10 because it's the most commonly used log. In fact, we call the dumb thing the common log.
So, if it was y equals log 10 to the third power, the derivative would be 1 over third.
Let's not go that far yet. I just want everybody to understand where the e came from. When I see natural log, okay, I'm about to write something that will, and you need to understand, I'm going to have pain in my brain from writing this. This hurts me. That hurts me to write this. I'm never going to write this again for you people. So understand this. Instead of writing this, we gave it its own special symbol because E is a special little dude. Do you guys know what E is used to model?
Yeah.
What?
Interest? No.
Sure, interest, right?
Compound?
Continuous growth, so it could be throw 2 rabbits in a room, give them some food. I could model population growth. It also models radioactive decay. Those are all what kind of processes?
Exponential.
Natural processes. So what do we call the log that goes with base E? Natural log. Ooh, look how creative we are. You guys are all with me? Did anybody tell you this before? No. So that's why we call it a natural log. When it has a base of E, we rewrite it as natural log. Because a base of E is used to model natural processes of growth or decay. So when I see natural log, I understand the base is E. But what's the natural log of E?
Cancels out.
Yeah. So then if I have natural log of x, its derivative is 1 over x.
Wow.
Huh? Wow is true. One thing I want to point out, so let me really highlight this for a moment. And now you understand why I had logarithm problems on that paper. So let me write this again. Does anyone see an issue if you look at the domains of those two functions? What's the domain of f? Up there. What's the domain of the f function?
Negative infinity.
0 to infinity. You can't handle negative inputs, right? Natural log. What's the natural log look like if you graph it? This is the one that it gets wrong, by the way. It doesn't do log. Yeah, natural log looks like this. Yes. You with me? So that's what? 0. So does it exist over here? No. What about 1 over x? What's its domain? Everything except 0. Do the domains match? No. So this is still true. I need you to understand this is still true. But if my function was this, I have to know that x has to be greater than 0. Does the function tell me x has to be greater than 0? No. The fact that it came from this does. Now here's what's interesting. Let me see if you guys are really cool with this. If my function had been this instead, my derivative would still be this. And what's nice now is, what's the domain of this function?
Positive infinity. Or 0 to positive infinity.
No. Why was this function's domain 0 to infinity? Because I can't take the natural log of a negative number. First thing I do to an input is absolute value it. So what's the domain of this? Every number except 0. What's the domain of this?
Every number except 0.
Hey. You guys follow? I need you to really get that. This is tricky, and this will make it easier when we get to doing differentiation in reverse. When we get to anti-derivatives, this will make it make more sense as to what the anti-derivative of 1 over x is. It's officially this one. Okay. This is the more general result. So if I have natural log of x, its derivative is 1 over x. If I have natural log of the absolute value of x, its derivative is 1 over x. It's just in this case, I have to know that I can't use x is less than 0. Or equal to 0. Okay. So we have expanded our ability of derivatives. We know how to take the derivative now of the log of any base of x. Okay. So let's push this. What is the derivative of this function here? We put the rule over here. So what's the rule say? What's the rule say?
1 over x to the second minus
1 over
x to the second minus 3.
the inside, right? So it's the derivative of log base b of stuff. 1 over stuff, natural log of base. Yes? Now we're not going to be done at that point. So let's see. How do I take the derivative of a log? 1 over the inside times the natural log of, well, in this case, what?
11.
11. Why am I not done?
Because you
What rule do I have to apply? Chain rule. So I don't give a shit what the function is. If there's more than just x inside of it, chain rule works. Thankfully, I don't think this happens as much, but some students felt like chain rule was connected to a certain kind of function. Chain rule is just always there. It's just always ready to go. I don't care what the function is. So, what's the derivative of x squared minus 3x?
2 minus 3.
And I'll just plop it on top. Bam!
It looks great to the face.
So this is just another rule. The way that you know x squared is derivative is 2x, you now know that natural log of x derivative is 1 over x. You just know it. So,
Wait, you multiply both sides by x squared minus 3?
sorry?
How do you get 2x minus 3 without the parentheses?
he did.
Because the inside is more than x, we did chain rule. The inside gets a turn.
Right.
Derivative of x squared minus 3x is 2x minus 3. And I just put it on the top because I just multiplied them, yes?
Yeah, okay, so I mean,
Yeah, yeah. But I didn't do it to the bottom, of course, because the bottom's going to 1. Okay. Is everybody with me? You guys all right?
Yeah.
So we keep expanding the straightforward functions that we know. We also are expanding the processes, like now we know implicit differentiation. The same way we know product rule and chain rule and quotient rule. Okay. So there's a whole another level. Oh God, what time is it? Ooh, I love it. You guys are awesome. Last thing for today. You with me? You're like, just say it and let's go out. Okay. How would I find the derivative of this here?
You could just draw a triangle.
Do it again.
What is it? Could you draw a triangle? Show.
Doesn't really help me in this case. I could draw a triangle. Wouldn't do shit for me yet. It might do shit for me later.
Oh, okay. Do you just find the derivative of tan? Do something
Like
like that.
inverse of there.
What did we do a second ago to figure out the derivative of log?
1 over.
What was the first thing we did? We rewrote it in its inverse form. Yes?
Yes.
Okay. So can't I rewrite this as x equals tangent y?
Yes.
Yes? So you guys see that? Do you guys see that?
Yeah.
Does everybody see that?
Yeah.
If I take the tangent of both sides, these guys kill each other because that's their job. Do I know the derivative of tangent?
Yeah.
What am I gonna have to be careful about?
The y. You gotta.
And that's gonna lead to what?
Chain.
Chain rule, dy dx stuff, yes? So here, I'll do one side. Derivative of x is 1. All right, you're welcome. So you guys take the derivative of tangent y. Go for it, don't say anything. Take the derivative of tangent of stuff. Tangent of y. Go for it. So you guys are just looking at me and that's freaking me out. Doing everything in your head. It's freaking me out.
Tan of secant squared y times dy.
Should be no negative. What's the derivative of what's the derivative of tangent stuff? Secant squared stuff?
Times dy over dx.
That's right. And then sorry. So then dy dx is 1 over,
Secant squared y.
right? Which I could write as cosine squared y. You guys see that?
Yes.
Because 1 over secant is cosine. And I have 2 of them. Now, this is not good enough. Because we started with a function of x. My derivative should be a function of x. So how do I figure out what the shit this is? I use the triangle. Love you guys.
I was gonna say that.
So what's this say? The
Put y over 1.
no, careful. Here's my inverse trick, yes?
Yeah.
Okay.
So that's what like.
So let me make sure you guys are cool with this. If I have, so y is the angle, yes? Y is the angle. The inverse tangent's x over 1, so that's x over 1. This would be, is everybody with me so far?
Yeah.
So the inside of the inverse tells me the ratio, yes?
Yeah.
Good. This is the angle, just like it is here, it's the angle. And then old Greek dude says this shit, yes? And then what is the cosine of y then? Let's just do that here. What's the cosine of y?
1 over rad x squared plus 1.
So what's the cosine squared of y? What's 1 squared?
1
And what's the square root of x squared plus 1 squared?
x squared plus 1.
Done. So what's the derivative of inverse tangent of x?
1 over x.
1 over x squared plus 1. So, wow. Tomorrow, we'll continue. We'll finish out the inverse trig stuff, derivatives. And then we'll get into, how do I package this? We'll get into section 310. I'm sorry, 3.9. Which is where we explore, all right, let me just tell you directly. It's calculus word problems.
Calculus what?
Word problems.
This is what you've been waiting for. You're like, come on, every math class is word problems. Yes. Today we did 3.5 and 3.6. And yeah, that's all.
So we got 3, 5, 3, 6.